Good morning. Hope everyone is feeling good and rested. So, yesterday I left you guys to work on the Chapter 10 homework, trying to get that as concluded as you feel comfortable with. Today, the main thing that I definitely want to focus on is starting Chapter 11, because Chapter 11 is we're going to begin looking at thermal energy directly. It's going to be more about the various things that thermal energy does and how we measure and quantify it. There's one of the two labs that we're going to be doing on campus tomorrow. One of them is going to be about thermal expansion. The second one is going to be about thermal energy. So my goal is to make sure to start Chapter 11 this morning so that information is in your minds and its formulas that we've covered. First, though, before that, how are you guys feeling? Does anyone have any questions or needs or concerns, etc.? All right.
I feel pretty good. I don't have any questions right now.
Okay.
Sorry about the puppy.
No, it's quite okay. There's also a puppy in my office with me because if I leave her in any other room unsupervised, she will eat something and then pee on it.
That's exactly what my puppy does.
They do be like that. Mine's coming up on a year old. She's hopefully growing out of the habit now.
We just got this dog. She was born in February, so
Oh,
she's like
wow.
old. Yeah.
Yeah, that's about as old as when we got Penny. Penny, come here. Come on, Pan Pan. Come, get over here. Say hi to physics.
Oh my gosh! Hi.
I've never shown Penny off to anybody. She's a chaotic little noodle. All right, so let's get started with Chapter 11. Please chime in with any questions or issues you have, even if they pertain to Chapter 10 homework. Let's see here. Oh, duh, I need to actually screen share in Google Meet.
This is Tazy. This is my little puppy.
Hello. You're so fluffy.
Yes.
Oh, so little.
Yeah, I know.
Giant. I can't tell if her paws are big or if it's just fur.
No, she tiny girl.
That is adorable. All right. So, I am always in favor of random physics questions and random puppy pictures, I guess. All right. So, Chapter 10 was mostly to do with temperature. We had to talk about thermal energy itself to kind of set up all the temperature stuff. Now we're going to focus back more in on thermal energy, namely how to calculate it and a few of the things that it specifically does that are somewhat independent of temperature in a few ways. So thermal energy itself is going to be our main focus for Chapter 11. And to start with, this is a image I've brushed over before. I want to pay more attention to it right now. Every object needs a certain amount of thermal energy to be at a specific temperature. But just because two things are at the same temperature does not mean that they have the same amount of thermal energy inside of them. For example, the question sort of posed on this particular slide is, imagine you have 1 cup of coffee that's at 100 degrees Celsius versus you have 1,000 cups of coffee that are all at 100 degrees Celsius. By virtue of this picture having more coffee in it, even though all the coffee's at the same temperature as the single cup, there's just more thermal energy in this picture because there's more material present to have that thermal energy. In another way, it's kind of like a battery. You can have two different sized batteries that are fully charged, but they're different sizes. They will have different amounts of energy inside of them, even when they're both full. So, the amount of material present, which I could also restate as the mass of material present, affects how much thermal energy is needed to keep a certain amount of material at a certain temperature. If there's more material, it takes more thermal energy for it to be at a specific temperature, and that's one reason why it takes a really long time to warm up a really large amount of water or melt a lot of ice. So, the mass of your object affects how much thermal energy you need to keep it at a certain temperature. But there's also another factor that determines how much thermal energy something specifically requires, and that's what that object is made of. At some point in your life, possibly just subconsciously in the back of your head, you've probably noticed that certain materials heat up faster than others. It's summer right now, and that means that everything exposed to direct sunlight is going to get real hot when left alone for a while. But if you sort of cast your mind to a hypothetical scenario where you're getting in the car to go to the lake for just a lake day. You get in the car, everything's warm, your car seat's, bearable to sit in because it's made out of leather or fabric, and then you reach over and you touch the metal part of your seatbelt. That's hot. That's miserable. But that metal has been in the same car as the seat you're sitting in. It's been touching the same temperature air as the seat that you're sitting in. It's been attached to all of the same pieces of car as the seat that you're sitting in. And they're all getting the same intensity sunlight, and yet they're at different temperatures. This weird difference in temperature will continue when you eventually arrive at the lake and you step out of the car and you step onto, say, concrete or asphalt with your bare feet, and a lot like the metal, that's suddenly a miserable experience. It's hot, you don't want to be standing on it, so you jump over to some grass. And the grass, despite being in the same sun, touching the same temperature air and ground, is not as hot as the asphalt is. And then you jump in the lake, and then the lake itself is the coldest thing you've interacted with since exiting your house. Despite it being in hot sun all day, the lake is still cold. The mass of each of these objects does play a role in how fast they'll heat up when absorbing energy from the sun, but what they are made of is equally important. Certain objects just naturally heat up faster with the same amount of thermal energy as other materials. And we, as physicists, because all the physics is turning things into numbers, we quantify this phenomena with specific heat. Specific heat, the concept of a material's specific heat, I'm going to circle this term down here, C equals Q divided by M times delta T. The concept of specific heat is a measurement of how much thermal energy it takes to heat up a certain material based on what it is made of and based on how much of the material is present. Thinking back to the lake example, metal, concrete, asphalt, those things all heat up quickly. They don't need a lot of thermal energy to increase their temperature. You can give it a small amount of thermal energy and its temperature will skyrocket. On the other hand, grass and water heat up very slowly. Grass heats up slowly because it's mostly made out of water. So water heats up very slowly. It takes a lot of thermal energy to change its temperature. That is reflected in this specific heat variable. The C term down here is it is a variable called the specific heat of a given material. Every different material in the known universe has a specific heat, and since there's infinitely many of them, you don't need to memorize them. There's a handy chart right here that demonstrates most of them, and you can always refer to this table. You don't have to memorize them. I only have one of them memorized, and it's the one for water since I use it all the time. So this chart here, specific heat of some materials at atmospheric pressure, lists a bunch of different materials, and then this first column here is the one we care about. It lists the specific heat of those materials in units of joules per kilogram per degree Celsius. Those are just the metric units that we like, so this is the specific column that we will be utilizing. The second column is more so used in chemistry classes. But we'll use the first one for right now. And for every different material, there's a different number here, and again, the smaller the number, the easier it is to heat up that material, because it takes less energy to change its temperature. The smallest number on this table is lead at 128, followed by gold, mercury, cadmium, which is a metal, copper, iron, so on and so forth. So all the metals on here tend to have really, really small specific heats. It doesn't take much energy to make them hotter. On the opposite hand, the biggest number on this table is that of water, 4,186. It takes a lot of thermal energy to warm water up, and that's one reason why it takes, if you put on a pot of water, it takes it a while to boil to be able to cook your noodles. But the fact that water takes ages to heat up is actually a good thing, because Earth is covered in water. And if water heated up quickly, then the sun would literally boil the oceans, and the planet would be uninhabitable. So, water is a very good heat sink. It can absorb a lot of heat without changing its temperature. And that's why it tends to be used in some cooling systems. So, this number, specifically, specific heat number, this number is specific heat. It represents the amount of thermal energy needed to change the temperature of a certain amount of a certain material. And we use this variable in this equation here, which is the same equation rearranged. The purpose of this equation, Q equals mc delta T, is to determine how much thermal energy is required to change the temperature of a certain mass of a certain material. Say you have 1 kilogram of iron, and you want to heat up that iron. You can use this formula to figure out how much thermal energy is required to heat up that iron. So the Q term, in all these formulas for the duration of this entire class, Q is going to refer to change in thermal energy. Q refers to heat flow. So for the sake of this particular formula, Q is going to mean either the amount of energy an object is gaining if it's heating up, or the energy the object is losing if it's cooling down. So it's always change in energy, it's always heat flow. It's positive if heat is going up, it's negative if heat is going down. M is mass in kilograms as usual. C is the specific heat, again the numbers from this table. And delta T is the change in the object's temperature. So again, the change in temperature of an object is directly correlated to how much energy it is either gaining to heat up or losing to cool down. And that means that the sign, the positive or negative sign on delta T, is going to match the positive or negative sign on Q. If you add thermal energy, you'll have a positive Q, temperature will rise, you'll have a positive delta T. And those signs are both negative if you're cooling down and losing thermal energy. It is a very useful formula that we're going to keep referring back to for the duration of all of our heat chapters this semester. And if there's no particular questions at this immediate time, we're going to start looking at a few examples of it today to make sure that it makes sense when we start using it in lab tomorrow and for the rest of the semester. So, straightforward example. At least this is straightforward for me because I eat a lot of pasta, so I have to boil a lot of water. We have a small camping stove, and we need to boil 1 kilogram of water. And usually, if you get water out of the tap, it'll start around a temperature of 20-25 degrees Celsius. So we have 1 kilogram that we need to heat up from 25 to its boiling point, and the boiling point in Celsius is 100 Celsius. So that means that we know the starting temperature of the water, its ending temperature, because we want to get it to its boiling point. We know its mass. We know that it is water. And we need to figure out how much thermal energy it needs in order to heat up. So, looking at our formula, Q equals mc delta T. We want Q. We know M. We can find delta T, because we know we need to end at 100 and we start at 25. And for the C term, for the way that these sorts of questions will work, the question will usually tell you what the object is made of. In this case, it's just water. And that's your invitation to tab back to this slide here and consult it for the specific heat of water. Again, it's the biggest one on the table, 4,186. You don't have to memorize any of these numbers, but out of all of them, you're going to use water the most. So it's the one that you will, if you end up accidentally memorizing any of them, it'll probably be the one for water. So, our mass of water is 1 kilogram. Our specific heat for water is 4,186. And our delta T for the water, our final temperature minus our initial temperature, we're starting at 25. We're ending at 100 since that's water's boiling point. Note again, the orientation, final minus initial, that's going to give us a change of positive 75. We are heating up by 75 Celsius. And since this formula specifically says delta T, we're allowed to use Celsius here. So I'm going to probably repeat this rule until the end of the class. Sorry. As long as it's delta T, you can use Kelvin or Celsius as long as the two match. If it's just T, you have to use Kelvin. But that's everything we need to find Q. We can do our multiplication, and that'll give us 313,650 joules, which is a lot. This is not a case where a number is big and then because it's in a weird unit and then I give you a better sense of scale. This is just a big number. It takes a lot of energy to boil water. Again, that's by design. Water's a good heat sink, and it's a good thing that it's a good heat sink because life on Earth would not be possible if it wasn't. Taking a quick pause for some water. All right. Let me know if there's any issues thus far, or anything that you would like me to repeat or go back over. I would like to, next I'm going to continue utilizing Q equals mc delta T in a few other situations. But there's one other formula I would like to show to you because we're going to be using it frequently in tandem with this formula here, Q equals mc delta T. In past science classes of yours, you've probably been made aware of the law of conservation of energy. Energy cannot be created or destroyed. It can change what object has it, it can change what form it's in, but if energy exists, it must continue to exist. The total amount of energy in a system remains constant. And that's still true for thermal energy. What that means is, if any one object gains some amount of thermal energy, some second object must also lose that same amount of thermal energy in order to make that possible. Consider whenever you touch anything and it feels, well, I'll just use my ice water. If I was to physically put my hand in my ice water, it would feel cold. And it feels cold because my body is losing thermal energy and the water is gaining thermal energy. If I lose 100 joules of thermal energy, that means that the water gained 100 joules of thermal energy. The same amount of energy exists, it's just moving out of me and into the water. So, any energy one object gains, another must lose the same amount. Excuse me. Sorry. And that's all this formula represents. This is just the comparison of the heat that one energy gains versus the heat that one object gains versus the heat that a different object lost to make that possible. Now, the way we're going to commonly utilize this expression is, on one side, we're going to be looking specifically at the factors for the heat gain or loss of one object. And then on the other side, we'll be looking at the factors of a second object that is involved in the thermal system. Because usually we'll be looking at one object that gets hotter and then comparing it to the object that lost the thermal energy to make the first object hotter. So the two sides will usually represent two different objects in thermal contact. And most commonly, we're going to be substituting these Q's with this formula, Q equals mc delta T. Since Q is mc delta T, that means we can take mc delta T and replace these Q's with it. So we're able to combine the two formulas together to specifically examine how the mass, specific heat, and change in temperature of one object affect the change in temperature of a second object based on its mass and its specific heat as well. And I'm going to show some examples of that. I'm going to show my calculations to give you some idea of what those calculations will look like. The one thing that I want to, the one additional thing I want to address about this formula before I show some of that sample math is this negative sign on Q lost. That is there for a reason. Specifically, the intention on the Q lost side is Q lost is inherently a negative number. If something is losing thermal energy, its temperature is dropping, its Q is going to be negative. This extra negative sign right here is designed to cancel the negative inherent to Q lost. Because if you don't do that, if this extra negative doesn't cancel the negative already in Q lost, then this whole right side would still be negative and therefore not equal to the positive number on the left side. Q gained is always a positive number, Q lost is always a negative number, and the positive and the negative can't technically be equal to one another. It'll interfere with your math if this extra negative sign here does not negate the inherent negative within Q lost. So a negative times a negative will make the right side positive in order to match the left side. So that negative is there for a reason, and I'm going to factor that negative into all of the math that I show you for how to utilize this particular concept. So don't ignore the negative. It serves a purpose. Ultimately, the right side will be positive to match the left. The math won't work unless you take that step. please chime in or interrupt me if you want me to go back over any of that. Next thing I'm going to do is we're going to look at how to work a few sample problems utilizing this principle, because there's a few different ways it can manifest. There's a few different ways I want to show you before tomorrow. Or, yes. So, let's say that you have a 50-gram piece of copper. So object 1 is a piece of copper. It has a mass of 50 grams, and its starting temperature is 120 degrees Celsius. You then take that copper and drop it into a bucket of water. So the water is our second object. That water has a mass of 1 kilogram, and its starting temperature is 21 Celsius. Those two objects, the copper and the water, are now in thermal contact. They're going to be exchanging thermal energy. This is very similar to if you've ever watched a history piece set in medieval times, or maybe even the Old West, where a blacksmith heats up metal in order to make something out of it. The metal's glowing red hot, and then you dunk it in water to cool it off. The metal will change temperature very quickly, but the water absorbs all of that thermal energy. That's going to be what happens here. We're putting hot metal in room temperature water to cool it off. And what we're being asked to find is what is the final temperature that these two objects are going to reach. If you'll remember, when we were talking about temperature, if two objects are touching, they're going to keep exchanging thermal energy until they end up at the same temperature. If you leave your hand in ice water, eventually your hand and the ice water will end up at the same temperature once there's been enough energy flow to melt all the ice and bring the water up to whatever temperature your hand is dropped to. So, for this example, both of the copper and the water will have the same final temperature. They are going to exchange energy until they reach the same final temperature. And that's, I'm going to show how to do that in the algebra. Whoops. So, now, and if my work here is hard to read, these notes are available on, excuse me, these notes are available on our class Brightspace page, and I can make the pictures available in higher resolution if you need that. I'm going to continue on from here. Q gained equals Q lost. If we're going to use this concept, we need to first identify which object is gaining thermal energy and which object is losing thermal energy. So, of the two things present, the copper and the water, the copper starts out hot and it's going to dump thermal energy into the water. So the Q gained side is going to represent the water, since the water is absorbing energy from the copper. So on this left side, I've replaced Q gained with MC delta T, but specifically for water. The mass of the water, the specific heat of the water, and the change in temperature of the water. Again, Q equals MC delta T, so wherever you see a Q, you can replace it with MC delta T. On the right side, the copper, I keep wanting to call it a bullet, the copper is going to lose thermal energy, so that's going to be the Q lost object. So we're going to replace this Q with MC delta T, but for copper. So mass of copper, specific heat of copper, change in temperature of copper. The subscript I'm using here is Cu, which is the periodic table symbol for copper. So, mass of water is 1 kilogram. Specific heat of water is 4,186. Excuse me. I've got a shortened version of the table over here to show the C for water and the C for copper. The change in temperature of the water, we don't know its final temperature yet. That's the point of this question, is we're going to calculate the final temperature. But we do know its starting temperature, 21 Celsius. So I'm going to leave it in the form of TF minus 21. On the copper side, we need to keep that negative sign there. That negative sign cannot go away until we factor it in and it cancels out. So I'm leaving the negative sign from Q lost on the front. So negative times the copper's mass, which is listed as 50 grams. This formula does require kilograms to work right. So 50 grams is 0.05 kilograms. Specific heat of copper, if we check our table over here, is 387. Notice that that is a much, much smaller number than the specific heat of water. It's actually higher than most metals, but still less than water's. And then there's the copper's change in temperature. It's going to end up at the same final temperature as the water, but its starting point was different. So this TF here is the same TF as the water's in this specific case. It's going to be the same variable on both sides. The starting temperature is different though, so it begins at 120 and it's going to end at our mystery TF. We don't know what that TF is. It's the same variable on both sides, and we're going to utilize that fact in the algebra, but it's worth considering. We know for a fact the copper is going to cool down. From our experience of the universe, it's a safe bet the copper is going to cool down. That means that this delta T in here, like the whole delta T term, would be negative. And again, this negative on the front that we kept from the original version of the formula is designed to negate the negative inside that delta T because it's cooling down. Our math wouldn't work if we did not factor that in. So I'm going to show in the next couple of lines what that looks like. As of this line here, we've plugged in every single number that we know, and even though the last remaining variable is in two different places, there's still only one variable left. So we can now successfully solve this for TF. On each side, I then distributed everything so that we just have fewer terms to work with. On the left here, we've got 1 times 4,186, and then times, open quotes, TF minus 21. So I just distributed the 4,186 into the parentheses term using the distributive property and wound up with this line down here, 4,186 TF minus 87,906, which is the product of C and the starting temperature of the water. So I've distributed everything that I could on the left side here, and we cannot reduce the left side on its own anymore. We got one term with a TF in it and one term that does not have a TF in it. So now we have to look at the left side and basically do the same thing there to try to get the TF out of the distributive parentheses that it's stuck in. So on the left, I also distributed the M and the C term into the parentheses. But again, keep in mind, there's this extra negative here that if we're distributing all this other stuff into the parentheses, that negative has to go with it. So we're distributing negative 0.05 times 387 into and across both terms of this parentheses. And so because of that, the product of doing that is negative 19.35 times TF plus positive 2,322. I've factored the negative all the way through. Normally the TF term is positive and the not TF term is negative, but because I factored the negative through, that is swapped. And we needed that to switch so that on the next line, as we send things across from the two different sides, everything ends up positive. As of this line, we are now freely able to add and subtract our terms across from one side to the other. And on each side, we have one term with a TF in it and one term that does not have a TF in it. So we want to get all the TFs on one side and all the not TFs on the other. So I'm going to recommend adding positive 19.35 to both sides. That'll send that second TF term to the left. And then adding positive 87,906 to both sides to send that over to the right. And after performing that step, you would end up with this next line. Both TF terms as positive on the left side, and both non-TF terms as positive on the right side. Now that the TFs are together, these can be successfully added. Since they're both functions of TF, you can add them together as normal. And since these two terms aren't functions of TF, they can be added together as normal. So add these together, and then divide by whatever is left times TF. And our final ultimate answer will be TF equals 21.46 degrees Celsius. It's a lot of lines of algebra to get here, but this is the correct answer. And I want to sort of compare it to what your expectations of real life would be. This final temperature here, 21.46, is only half a degree warmer than the water was to start with. The water only heated up by half a degree Celsius. Meanwhile, the copper went from 120 Celsius to 21.5 Celsius. It cooled down by nearly 100 degrees Celsius. This matches our usual expectation of reality. Water's a very good heat sink. We specifically use it to cool things off. So if you take a tiny, tiny piece of metal and dump it into a lot of water, the water's temperature is not going to change. Hardly at all. But the metal's going to cool down a lot because it doesn't have a whole lot of thermal energy in it to begin with. It doesn't take a lot of energy to make metal hot. That same amount of energy, when you take it out of the metal and put it into the water, isn't going to change the water's temperature much because of its high specific heat. But additionally, there's a lot more water in this situation, 1 whole kilogram, than there is copper. There's only 50 grams of copper here. So the water had more mass and a higher specific heat, so it was never going to change temperature very much. This would be like dumping boiling water into the ocean. The boiling water will cool off immediately, and the ocean won't heat up at all. So that's sort of the comparison here. And so ultimately this number, after all the steps of algebra needed to get it, makes sense. And so this is proof that the steps that we did worked. Let me know how this feels. And again, also let me know if my math is hard to read or you want me to reiterate some steps. I can additionally rewrite similar work to try to make it... I can rewrite some similar work. We're going to do some more samples involving this. And when we also meet up for lab this week, I can also put big samples on the board as well. So let me know how you're feeling. Let me know if you're shaky on this. I would like to go over one more quick example that'll demonstrate sort of how we're going to use this in lab tomorrow. So this is going to be a slightly different example that should actually be quicker to work because there will be fewer steps to the algebra. But I want to show you this one because it's specifically the method we're going to be using in our lab activity tomorrow. So, different example, a metallurgist heats a 100 gram sample of an unknown grayish metal up to 800 Kelvin and drops it into a 1 kilogram bucket of water. The water begins at 25 Celsius and it ends at 26.5 Celsius. So what is the unknown sample of metal most likely made of? This is referring to an old trick that scientists used to use to help identify what material something was made of. Since every different material has a different specific heat, if you can experimentally determine what specific heat something is, you can consult the table and try to guess what that material is made out of. And this is this historically has been specifically handy for metallurgists, which is the term for the type of scientist that studies metal, because a lot of metals look really similar. They tend to end up being hard, shiny, grayish blobs, and they're kind of hard to tell apart just by looking at them. So this is a trick that was and is still used to quickly try to figure out what something is most likely made of. If you can figure out its specific heat, you can track that specific heat and try to figure out what the material is most likely. And that's going to be what we do in lab tomorrow, and that's what I want to demonstrate for you real quick. So, this would have the same starting point as the previous question. One object is going to gain thermal energy, another object is going to lose thermal energy. And we're still comparing the energy gain of water compared to the energy loss of a piece of metal. So the gained side is going to look pretty much identical. We've got 1 kilogram of water, which will determine the mass and the C, and then the temperature change of the water. What's going to be different here is, and again, this is going to be what we do in lab, so keep in mind, we actually know both the final and initial temperatures here, because in this particular lab experiment, we're able to measure that change as it happens. So TF is no longer an unknown. We now know what the temperature change is for the water. It increased by 1.5 degrees. So there's no longer any unknowns on that left side, and that means that we can successfully calculate in its entirety how much thermal energy that the water gained. So no unknowns left there. We can find a number. It's more straightforward than the previous example. On the metal side, we know the mass of our metal, 100 grams is 0.1 kilograms, and we know the change in temperature of our metal, because we know its starting point, 800 Kelvin, and we know its ending point, which will be the same temperature as the water, because they're touching and they're going to continue exchanging energy until they reach equilibrium. So, like before, the metal will have the same TF as the water, it's just that now we know what it is. So, the metal's change in temperature, it's going to go to a final temperature of 26.5 from an initial temperature. One small trick that I want to point out to you, because it'll probably come up in the homework, is that because the formula calls for delta T, you are allowed to use Celsius here, but you cannot mix and match. Our starting temperature was listed as 800 Kelvin, and our ending temperature is listed as 26.5 Celsius. You can use Celsius here, or you could use Kelvin, but you can't mix and match. The two temperatures you plug into the delta have to be in the same scale. So what I've done here is I've plugged in 527 as our starting temperature, because that's 800 Kelvin in Celsius. I subtracted 273 from 800 to get 527. So this is our Celsius starting point compared with our Celsius ending point. Keep that in mind. That means the only unknown on the right side is now specific heat. The goal of this question is to find the specific heat of our mystery metal to help us identify it. So we're going to leave the C term as it is for now, and we're going to multiply everything else together. We can get a whole number, negative 0.1 times our delta T. It's going to give us positive 50, basically, times our unknown C. C is the only unknown left. We can successfully solve for it using this method, and we get a final answer of 125.45 joules per kilogram degrees Celsius. Once you have this number, you can then look at your table to try to see which other number it's closest to. And of all the numbers on this table, the one that 125 is closest to is lead. Lead's entry is 128, so that's as close as it gets. And lead matches the physical description a sample of unknown grayish metal. So, based on the specific heat and based on what we were told about the metal's physical properties, we can use this method to identify that it is most likely lead. Of the 2 labs that we'll be doing on campus tomorrow, first one will be thermal expansion. The second one is going to be this question. We're going to be physically doing this metallurgy trick, and your goal will be identifying certain metal samples to try to figure out what they're made of using this tactic. So, let me know any questions, needs, opinions, concerns, or haikus that you may have. I think that this is a okay breaking point for right now. So if you do have any issues, please let me know. I'll be in here for the next hour. I encourage you to take a quick break, get a snack, go to the bathroom, and begin looking at the Chapter 11 homework, seeing where the information from today can come in handy there, kind of get started on it. And if no one has any questions or issues right now, I will be right here for the next hour or so if you come back in with any. And if you don't, then I will hopefully see you tomorrow for lab, and hopefully it'll be a good time. Bring closed-toed shoes. There will be boiling water involved.